We're going to take a look at section 1.6. So the guided notes for this are in Canvas if you want to use them. The name of the section is Solving Other Types of Equations. So remember this entire first chapter. I'm going to abbreviate equations here. This entire first chapter is all about solving lots of different types of equations, and then we're going to do some inequalities in the next section. But recall in the last section in 1.5, we looked at quadratic equations specifically and how to solve quadratic equations. So in addition to solving quadratic equations, there's 4 other types you need to know, and we're going to cover those in this section. So the first type is a polynomial equation, and we're going to actually solve that by factoring, and I'll show you that in a few minutes. Then we're going to look at square root equations, or I'm going to say radical equations, because they don't necessarily have to be a square root, but they have a radical somewhere in the equation to start with. The third type we're going to look at are absolute value equations. And then the fourth type that we're going to look at is called rational exponent equations. So in other words, equations that have exponents that are rational or fractions. So let's go ahead and start example 1. And example 1 is an example of a polynomial equation. So let's take a look at it. So we've got 3x to the 4th equals 27x squared. And what we want to do is we want to solve this equation. It's tempting when you see a question like this to think about maybe dividing both sides by something to see if something will cancel out. That's not the way you want to handle this, though. Instead, what you want to use, remember, is the zero product property. We did this when we solved quadratic equations by factoring. So we want to get everything equal to 0 and factor. You want to try to make the term with the highest degree term as positive. So since that's on the left side, I'm going to go ahead and move the 27x squared over to the left side. And so we have 3x to the 4th minus 27x squared equals, of course these go away, we want it equal to 0. Now we're going to take what we have and we're going to factor it. You notice we have 2 terms, and there is a GCF of 3 and x squared. Remember the lowest power term that they share, that's part of your GCF. So I'm going to take out 3x squared. And since there's 2 terms here, I need 2 terms in my parentheses. So the first term, 3x squared times x squared, gives me 3x to the 4th. 3x squared times negative 9 will give me negative 27x squared. And if that can factor further, go ahead and do that. Hopefully by now you see x squared minus 9. That's a difference of 2 squares. So let's break that down into x plus 3 times x minus 3. So now we have 3 factors that have variables in them, 3x squared, x plus 3, and x minus 3. So the zero product property says to solve this, we can set each of these factors equal to 0. We're going to solve each of these equations individually. So the first one I'm going to divide by 3. Of course, 3 divided by 3 goes away. 0 divided by any number, of course, is 0. You can think square root if you want to, but x equals 0 is going to be the first solution. Next solution, we're going to subtract 3 from both sides. So I can end up with x equals negative 3. Last solution, I'm going to add 3 to both sides. So I end up with x equals positive 3. And so this equation had 3 distinct solutions, 0, negative 3, and positive 3. Okay, let's take a look at example 2. So example 2 is another example of a polynomial equation. Polynomial, by the way, means many terms. So if you have an equation with several terms where the variable is an x or some other variable and the exponents are positive numbers, that's going to be a polynomial equation. And so whenever you have a polynomial equation, just like in the last example, we want to set everything equal to 0. The x cubed term is the highest degree term, and that's already positive, so I'm going to leave it where it is and move everything to the left side. So I'm going to subtract 4x and subtract 4. We can go ahead and do it in one step. Those go away, and write your answer in descending order. We get x to the 3rd plus x squared minus 4x minus 4 equals 0. And now recall that when you have 4 terms and you're factoring, that's when you want to group factor. So I'm going to group the first two, and remember when I group factor, if that third term is negative, I like to leave that negative with it. Take out the GCF of the first two. Hopefully you see that it's x squared. So that's going to leave me with x plus 1. Take out the negative 4 from the second two, and remember when you group factor, what's in the parentheses has to match, and it does. If I take out a negative 4, I have to multiply it by x plus 1 to get negative 4x minus 4. That matches the original x plus 1 I had. One more step to factor. I need to take out the common factor of x plus 1, and then my other two factors are what's left, so I have x squared and minus 4, and all of that's equal to 0. Hopefully you noticed there's a difference of squares, so I recommend breaking that down as far as you can. Anything that can be factored, go ahead and do that. And so now we have 3 factors that we're going to set equal to 0. So we have x plus 1 equals 0, x plus 2 equals 0, and x minus 2 equals 0. So my solutions are x equals negative 1, x equals negative 2, and x equals positive 2. So that was the zero product property that we used to solve that. The next example, example 3, is also an example of a polynomial. I'm going to move the page up here. So let's see what we have. We've got x to the 4th minus 8x squared minus 9 equals 0. And they want us to solve this equation. It's already equal to 0, so that saves us a little bit of work there. We have a trinomial here. There's no GCF in this expression, so I can't take out any kind of a GCF. This is actually in the form of a regular trinomial that we're used to seeing. And so this will factor into 2 binomials. And let me show you just real quick, kind of off to the side. If this equation, if the polynomial had been x squared minus 8x minus 9, and we factored it, we would have had what? X and x minus 9 positive 1. This is going to have the same structure. But instead of having x and x, we need the first terms to multiply to x to the 4th and multiply to x squared in the middle. So that means we're going to use x squared and x squared. But we still need the minus 9 and the plus 1 because negative 9 and positive 1 multiply to negative 9 but add to negative 8. See that there's also a difference of squares. We have x squared minus 9. We can break that down into x plus 3, x minus 3. X squared plus 1 is a sum of squares. We cannot break down a sum of squares, so I'm going to leave that the way it is. So now we're going to take these factors and we're going to set everything equal to 0 like we've been doing. So I get x plus 3 equals 0, x minus 3 equals 0, and x squared plus 1 equals 0. So my solutions, we get x equals negative 3, x equals positive 3. Now to solve this, I've got a little kind of mini square root equation here, or rather equation I can solve using the square root method. I'm going to subtract 1 from both sides, so I get x squared equals negative 1. So remember back to the last chapter, if the thing that's being squared can be isolated, we can do that, and then take the square root of both sides. So I have x equals, and remember anytime you insert the square root, you need to include plus minus. Square root of negative 1, don't forget, is I. So this problem is going to have 4 solutions, x equals negative 3, x equals positive 3, and x equals positive and negative I. The next example is an example of a square root equation. So we've got x plus minus the square root of 26 minus 11x. And actually I should call this a radical equation. I think that's what the term our book uses. It's got a radical in the expression. So whenever you have a radical in your equation and you want to solve for the variable, first thing you want to remember is I need to isolate the radical. So in other words, get that radical by itself. If there's something in front of it, something after it, something being multiplied, we got to get rid of all of that first. So you notice this x out here needs to move to the other side so that I can isolate the square root or the radical. So I'm going to subtract x from both sides. So I have the square root of 26 minus 11x equals 4 minus x. Now that I've isolated the radical, to solve this, I'm going to square both sides. In other words, this is a square root, so I'm going to raise both sides to the second power. I can square something as long as I'm doing it to both sides of an equation. When you square a square root, of course, that leaves you with what's under the square root. Now be careful here. 4 minus x squared, that's a binomial, so I have to FOIL that. So I'm going to come off to the side and write it twice. And so if we FOIL that, we get 16 minus 4x minus 4x plus x squared. So I'm going to combine those like terms and come back to my equation. I have 16 minus 8x plus x squared. So now I've got this equation. It's actually a form of a quadratic equation. It's a little bit messy, but it's a quadratic equation because we've got that x squared term. I want to get everything to one side and see if this will factor. Since the x squared term is on the right side and it's positive, I'm going to go ahead and move everything to the right side and set it equal to 0. So I'm going to add 11x to both sides. So I have 26, those are gone, equals 16 plus 3x plus x squared, and then I'm going to subtract 26. So I have a 0 on the left side equals, now I'm going to rewrite this in descending order so it looks like what I'm familiar with, so I can see if it factors. So I have x squared plus 3x, and then 16 and negative 26, of course, is negative 10. Unfortunately for us, this does factor, and I won't give you any of these that don't. So either it will be an equation that doesn't require quadratic methods and you can just solve it like a regular linear equation, or if it's quadratic like this, it'll give you something that factors. So I'm going to have an x here and an x here. We need numbers that multiply to negative 10 but add to 3. So that's going to be 5 and 2, positive 5, negative 2. So now we use the zero product property. That never goes away. We're going to use that a lot this semester, so get comfortable with it. So we're going to have x equals negative 5 and x equals 2. Now with radical equations, there's one caveat, and this is the only time you have to worry about this is when you're working with these radical equations, and that is that you must check your solutions. And this is really important. There's going to be times where you're going to solve the equation, you're going to square both sides like we did earlier, go through all these steps and get numbers, and they're not going to be actual solutions. Sometimes that happens. It's called an extraneous solution. And so to handle that, make sure we don't run into that, we need to check our solutions, particularly when we have two solutions like we did here. So I'm going to go back to the original equation. So the original equation, recall, was x plus the square root of 26 minus 11x equals 4. So let's start with the x equals negative 5. So I'm going to substitute in negative 5 wherever there's an x. And what we want to check to see is if that simplifies down to positive 4. So we have negative 5 plus the square root of 26. Negative times a negative is positive 55. So that's negative 5 plus the square root of, I believe that's 81, which is negative 5 plus 9, which does in fact equal 4. So the negative 5 checks out. Let's come off to the side and work on the negative, or the positive 2 rather. So I'm going to do the same thing. I'm going to replace x with a 2. And we want to see if that simplifies down to 4 as well. So we have 2 plus the square root of 26 minus 22. We want to know, does that equal 4? 26 minus 22, of course, is 4. So I have 2 plus the square root of 4, which is 2 plus 2, which does, in fact, equal 4. So we are good to go. Okay, so the next type of equation, we've done polynomial, we've done radical equations. So the next type we need to take a look at is absolute value equations. So example 5 in the guided notes is an absolute value equation. We've got 2 times the absolute value of 3x minus 1 plus 4 equals 8. So just like with the radical equations, the first thing you want to do is isolate the absolute value. So that's important. Let's isolate the absolute value. So if you have stuff in front of it or after it or whatever, you got to get rid of that. You got to solve for the absolute value before you could do anything else. So to do that, I'm going to subtract the 4 first. So I have 2 times the absolute value of 3x minus 1 equals 8 minus 4, which is 4. And then we need to get rid of the 2. Of course, take note that absolute value is not the same as parentheses. I can't distribute the 2 or something like that. The only thing I can do is move the 2 to the other side. So since it's being multiplied by the absolute value, I'm going to divide it to get it to the other side. So I have the absolute value of 3x minus 1 equals 2. And now we've isolated the absolute value. So what I want you to think about is how absolute values work. Absolute value says whatever's in the absolute value, I want to take that number and I want to make it positive is really what ends up happening. It's the distance that expression is from 0. So in other words, let me say it a different way. If I just gave you, forget the question for a second, if I just gave you the absolute value of 2 and I said simplify that, tell me what that's equal to. You tell me 2, right? Likewise, if I said what's the absolute value of negative 2? And I'd say simplify that, you'd tell me, well, that's also 2. So the moral of the story here is this expression that's inside the absolute value, there's 2 possibilities for what it can equal and give us a solution to this equation. It could equal 2, or it could also equal negative 2. And when we take the absolute value of it, we would still get 2. So to solve this, we're going to drop the absolute value and we're going to set up 2 equations. So I'm going to take the inside, the 3x minus 1, and I'm going to set it equal to 2, because that's one possibility. It could equal 2. And then I'm going to also set it equal to negative 2, right? Because that was another possibility. It could equal negative 2. You're not going to change anything on the inside of the absolute value equation. If there's a negative, there's a negative. Leave it alone. You're just going to take whatever that expression is and set it equal to the positive and the negative of the number we're trying to find it equal to. Then you're going to solve each equation individually. So I have 3x equals 3, divide by 3. I get x equals 1. Over here, I'm going to add the 1. I get 3x equals negative 1, divide by 3. And I get a solution of x equals negative 1/3. So absolute value equations will have 2 solutions. There's some quirky cases where it won't, but most of the time you're going to have 2 solutions. No need to check these. Those are your solutions. You're good to go. Okay, so the last example is the last type of equation we need to be able to solve from this section. So we've done polynomial, we've done radical, we've done absolute value equations. Now we're going to do ones that have a rational exponent. So we have x plus 5 to the 3/2 power equals 8. So this is that rational exponent equation because the exponent is a rational number or a fraction, which is 3/2. So the way we're going to solve this, first of all, you want to isolate the thing that's being raised to the power. If there were a number in front, I'd need to divide it to the other side. If I were adding or subtracting a number, I would need to move it to the other side. But in this case, I just have the x plus 5 raised to the power expression. It's already isolated. So I'm going to go ahead and proceed with the next step, which is to raise both sides to a power that will essentially cancel out this 3/2. Let me show you what I mean. If I raise both sides to a power, I want you to think about what number I would have to raise this to over here to get rid of the 3/2. Remember that you multiply exponents when